This video is for the kids who missed my class for a week last week for reaction kinetics SL. Okay, rate of reaction, the unit is actually mole per dm cube per time. So the time can be second or minutes. But there are other ways, indirect ways to measure the rate of reaction, whereby we can also measure volume, we can also measure mass. So it's not limited to just concentration, but the official way or the actual unit or rate of reaction is concentration. Okay, how do we get rate of reaction from a graph? So this is a graph of time and concentration. Okay, concentration here is in mole per dm cube, and time can be in seconds or minutes. So where do we get the rate from this graph? We draw a tangent and we calculate the gradient. We draw a tangent and calculate the gradient. Okay, so if they ask you what is the initial rate of reaction, so you have to draw a tangent that just touches the time zero and don't touch any other parts of this curve. And when you get the tangent for time zero, then you calculate the gradient, that is the initial rate. Okay, so in exams, of course, students will all draw a different angle here, right? So they will accept a range of answers. But if you draw and calculate one that is out of the range of the marking scheme, then you do not get a mark. Okay, from your textbook, this is the Pearson textbook, not the one we have in school. You can refer to the soft copy of the Pearson textbook, or if you have the Pearson textbook, this is the way to get the rate of reaction at time 120 seconds. So they draw a tangent here. See, it only touches at 120, so the rest of the parts should not touch the curve. And then you calculate the gradient. So the unit would be in mole per dm cube per time or per second here. Another example, they calculate the initial rate here by having the tangent at time zero, calculate the gradient, that's initial rate. And they also show you how to calculate the rate at 90 seconds. So the rate is all different. At the very beginning, it's very steep. It means that steep means it's fast or high rate of reaction. And when it's lesser, it's not as fast. And then like this, less steep means it's slow or low rate of reaction. And if it flattens like that, it flattens horizontally, it means that the reaction might have ended or stopped, or there's no more reactants. Okay, so you do get graphs that go downwards or upwards. So if you have downwards like that, it means they are plotting against the reactants. These are the reactants because as time goes by, the reactant got lesser and lesser, so lower in concentration. And as for the products, that C is the product, you get more and more products over time. But you will see that the rate is the same here because it's fast, fast, and fast, and then it becomes slow, slow, and slow. And here, approximately here, is when it flattens, so that's when the reaction stops. Okay, there's many ways to measure rate of reaction. This might give you some ideas for your IE. Okay, ways to measure rate of reaction. If it's in a solution form, so if your reactants are in solution form, you can measure the concentration. Okay, metric is a way to measure concentration, and it's a little bit more troublesome. You need to measure the concentration over a range of time. So you need a graph, and this x-axis is the time. It could be in seconds or minutes. Let's just put seconds there. For example, maybe 1 minute, 60 seconds, 120, 180, and so on. Okay, titrimetric means what? Means titration. So for example, I have a solution here, standard solution of known concentration. Um, let's say I have a reaction of A plus B, you get C plus D. So A and B are the reactants. Here's where I'm going to run the experiment, the reaction here, A plus B. So a reaction will happen in here. And at the same time, I need another reactant whereby it can react with, this is separated from the main reaction that we are doing a research on. So we are trying to get the rate of reaction of A and B, not this other reaction. This other reaction is for you to calculate the concentration of A. So let's say I have another solution here, E. It will form something else, doesn't matter. And it gives you a color change here so that you can do titration. So you have an endpoint to look for. Okay, so let's say this is the standard solution of known concentration of E. So what is E? E is something that reacts with A. Let's say 1:1 to make it simple. Okay, so what you're going to do here is you're going to add in the A and the B, let it react, have a stopwatch. Okay, and when it reaches 60 seconds, you have to draw out some of the reaction and you have to reactants, the solution, and you have to stop the reaction. Okay, so let's say I draw out 10 centimeter cubes of the mixture of A and B. It's still reacting, it's not completed yet. So A is still decreasing in its concentration. B is still decreasing in its concentration because they're all forming C and D at that time. So at minute number 1, they haven't finished reacting yet. Okay, so once you withdraw that 10 centimeter cube, you will have to quench the reaction, quench or stop the reaction. So the word to use for stopping the reaction is to quench the reaction. Okay, why do we stop the reaction? Because we want to know the concentration of A at that point, at 60 seconds. So at 1 minute. So we have to stop the reaction. How do we stop the reaction? You need to see what kind of reaction is this A plus B, is C plus D. So if this is a reaction that is, for example, heat catalyzed, how do you stop the reaction? You stop it, quench. You quench the reaction or you stop the reaction by putting ice cubes. Or maybe it is acid catalyzed. So to stop the reaction, maybe you add sodium hydroxide. You neutralize it so that it has no catalyst, so that reaction stop there. Okay, so you draw out some of the mixture of A and B, the one that are still reacting. You quench the reaction, and then you titrate with this standard solution of known concentration of E. Okay, so I said the ratio is 1:1, right? Just to make the example simple. So M of that A and V of the A will be equal to M of E and V of E because the ratio is 1:1, right? I put the example as 1:1. Of course, you might have a standard solution that's not 1:1, then it will be a more complicated concentration, but that's not what we're focusing on here. We're not doing stoichiometry today, so just 1:1, okay? Okay, so what do we want to get here? We want to get the concentration of A because at 60 seconds, we want to know how is the concentration of A then? Because we know the original concentration of A and B, so I can plot the initial concentration here. Okay, but I don't know at time 60 seconds, what is the concentration now after some time, after they have reacted? Okay, so what I do is, I know the volume of A. Volume of A is this, 10. And M of E, I said known concentration, right? So just put that here. And what is the V of E? That's the titration value, the titer. Okay, so since I have the M and the V of E, and then I have the V of A, so I can calculate the M of A, and that shall be what I'm going to plot here, the concentration of A. All right, put square bracket. So square bracket always means concentration. Okay, then what do I do next? It doesn't end there. So after 2 minutes, you have to do the same thing. So this is 1 minute. And then the second minute, I gotta repeat the same thing, draw from the same place because this one was not quenched. So the reaction was still going on just now. So after 2 minutes, maybe you will need help. Obviously, you can't do this alone. So after 2 minutes, you quench it also, stop the reaction and do another titration. Calculate what is the new concentration of A, plot it there. And then after 3 minutes, so you see, you might need help here. After 3 minutes, do another round, draw it out, quench it, do your calculation, do titration, blah, 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 and plot it there. So you'll need to do it over a period of time. You might get a curve, you might get a straight line down. So that is the result of the experiment. Okay, next methodology to find the rate of reaction. This is for reactions that involve liberation of gas. So for example, carbonates, so calcium carbonate. This is just an example, okay? I'm not fixing anything here. Just an example of a reaction that can form gas, or it will liberate carbon dioxide here. Okay, so this will be liberated. Okay, to measure the volume of gas, you'll need gas syringe. So this connected the gas syringe. I'm pretty sure you've seen this before in IGCSE. Okay, but there are some difference or some details added that we don't use the way we measure in IGCSE. We need to be a little bit more specific. Okay, if you recall what you learned in IGCSE, especially for the last 6 marks, when you're doing a rate of reaction setup in IG, you can either say fix the time, how much gas volume that is gotten from, say, 120 seconds. So you wait for 120 seconds, and then you read the gas syringe, how much of gas is gotten. And then you repeat the experiment with, say, a different concentration of HCl. And then maybe it's more concentrated now. So you know that, oh, okay, a higher concentration, I should get faster rate of reaction. So in 120 seconds, maybe you get more gas. So that's how you do it in IGCSE, right? Please don't do that in IBDP. It's not detailed enough. Okay, there was another way also. What is the time taken to form, say, 100 centimeter cubes of gas? So you just need to read the stopwatch. So when it reaches 100 centimeter cube of gas, and then you read the stopwatch. The shorter the time, the faster the rate of reaction. So you're expecting, like, if I double the concentration of HCl, I'll get a shorter time. So these are what you did in IG, which is not detailed enough for IBDP. So please don't do this anymore. It's correct, it's just not detailed enough. Okay, so how do we do this in IBDP? It's actually similar. The setup is similar. It's just that this time you need to have an interval of time. So how much gas is produced over a period of time? So let's say here time, seconds. Again, I'm going to plot something like what we did just now, 120, 180, blah, blah, blah. And here would be the volume that you read from the gas arrange. So originally, there was no gas in the gas arrange. And after, say, 60 seconds, you read the gas arrange. After 120 seconds, read the gas arrange. After another 60 seconds, read again. After another 60 seconds, read again, read. Okay, so in IB, you always want like a graph. Okay, the calculation, you might get the same answer as IG, but the methodology is like, it's more detailed. I would be able to find out what is my rate of reaction at time 90. I would be able to find out my rate of reaction at somewhere in the middle here. By doing what? By drawing the tangent and calculating the gradient. Okay, alternatively, you can also do this with an inverted measuring cylinder, which you're also exposed to during IGCSE. So it's like a pipeline to an inverted measuring cylinder. I'm pretty sure you've seen this in your papers in IGCSE. Oh, my drawing's not nice. Okay, you get the idea, right? So the inverted measuring cylinder, and as the gas is produced, the water level will go down. Okay, but make sure if you want to do this method, make sure that the gas is not soluble in water. Gas, yep, that is not soluble in water. I mean, I'm sure there are some questions where they will do this method for a gas that is soluble in water. Maybe they'll ask you for what kind of improvements to do. Then you can say, oh, okay, this gas is soluble in water. It's not a great idea to do this measuring cylinder over inverted over water. Instead, we're going to use gas syringe. Okay, so they might ask you in a sense of improvements of the methodology. Okay, because it liberates gas, there's also another method, which is to measure the mass. Okay, you've also seen this in IG papers before. I think it was in the multiple choice where they put a stopper here, and then maybe that's A, and then B, they put a cotton. So the way to do it is to put a cotton, not a stopper, because if it forms gas, then you put a stopper there, the glassware might break, sort of explode. It breaks because the pressure is too high inside. Okay, but why not I just leave it open? Okay, the reason we don't want to leave it open is that I don't want the mass of the acid to spray out, then we will not record that mass. Instead, we get mass loss from the acid, which is an error actually. So we put a cotton there so that the acid is trapped on the cotton, so we still catch that mass, but the gas can escape. So there will be a mass loss. Okay, so how do we collect data for the rate of reaction for this kind of experiment? Again, you need a graph always. And here would be the mass. Okay, so you record the original mass, and after 60 seconds, it can be 30. Okay, I'll vary my example. It can be 30. It's easy to record. Just record more readings. 90, 120, 50, so on. Okay, so after 30 seconds, read. After 30 seconds, read. After 30 seconds, read. After 30 seconds, read. Okay, so you might get a curve or a straight line depending on your experiment. So it's not fixed, okay? Okay, next is colorimetry. Colorimetry is something like what we have in the lab, is to measure color intensity to represent concentration. So you see, we've been doing these experiments that are not concentration. Just the first one is concentration, right? And then the rest, the readings are not in concentration. This is in cm3 volume, and then the other one in mass, and now it's in color intensity. Now, all these are indirect methods to measure concentration. So we know that if the color is more intense, it means it's concentrated. The color becomes lighter or more see-through, then maybe the concentration has decreased. Okay, so it has to be a reaction whereby there is color to be seen. So same goes, if you want to do an IA using our instrument in the lab, you will need something that has visible light, as in there's color. Okay, so I'll give you an example here. Propanone is something that has no color. It's an organic compound. And then iodine, you know what's iodine's color, right? And then there's the product, also colorless. And HI, you know, it's there's no color. So in this case, I can only measure the I2. I can't measure the other. So I can't measure the product because there's no color. Okay, so it's only suitable for anything that has color. So I can only get a graph that goes down because only iodine has color. So if I want the rate of reaction, I want to know that if I change the concentration of iodine, what happens to the rate of reaction? And I want to know if I vary the concentration of, say, a propanone, what happens to the rate of reaction? So the machine does the intensity, the reading for me. I'm not using my own eyes, but the machine does it for me. So this is time. And this side is like the color intensity. So it's sort of the concentration of the I2, but the machine reads the concentration for me. Okay, so let's say this is 3 mole per dm cube, initial concentration of I2. Okay, over time, it's going to go down. It could be a curve, it could be a straight line. You learn that in HL. Okay, let's say I get a line like this, let's say, example. And let's say I were to repeat this experiment with another concentration of I2, but then I repeat it with 2 mole per dm cube. And if I find that the rate of reaction is not disturbed, is the same, sounds like not a very good IA, right? But actually that does tell you something. It shows that the rate is not dependent on the concentration of I2. So how do I get that here? You see, the gradient here is the same as this, which means if I have a 2 mole per dm cube I2 or a 3 mole per dm cube I2, I get the same rate. Okay, so if same gradient means same rate. Okay, or I can repeat this experiment with a different concentration of propanone. But this machine can only measure the concentration of I2. Okay, so let's say this was done with CH3COCH3 of 1 mole per dm cube. So let's say you repeat the experiment using a propanone of 2 mole per dm cube. So you'll see that maybe it becomes more steep. So what does that tell us? It tells us that as I increase the concentration of propanone, my rate of reaction increased. So these are the information that you can get from this type of graph. Okay, the last one, not much details in it. The last one is change in concentration of ions. If you read the textbook, there's not much details in it. It's just if the reactants are ions. So there are 12 ions here. It's 1 here, 5 here, and 6 ions here. There's a lot of ions here. So check the conductivity over time. So always over time, same as the rest of the experiment. So conductivity. Okay, I'm not sure what to measure conductivity with. You can just say like a conductivity sensor or a meter that can measure conductivity. Okay, so same thing, over a period of time, you have to measure it. So in this case, the reactants are the one that has charge. So the conductivity would decrease over time. Could be a curve or a straight line. Okay, but if you have something like having more charge at the product side, okay, whatever. So then your graph would go upwards because it becomes more and more conductive over time because there's more and more ions. Okay, those are the methods that you should know, or roughly the methods are, it's supposed to inspire you to think of more methods to measure rate of reaction. Okay, the next part that you missed was collision theory. Collision theory, you already covered this in IGCSE. Not much difference. You still need particles to collide before they can react, same thing. Not all collision will lead to a reaction. You've learned that before. They must possess at least a certain amount of energy that we call activation energy. You have learned that before. Okay, particles must approach each other in a certain orientation or certain steric effect. Okay, what does that mean? That means the positioning. So if you have a particle, say something like this, and maybe they are, maybe it's a molecule, okay? So perhaps if they meet this way, then maybe a reaction happens. So this is the orientation that is preferred to for the particles to react. So if the particles were to meet this way, maybe it's not going to react. Okay, or if they are colliding like heads on, they will react. Maybe if they're 90 degrees from each other, they just bounce off each other, so they might not react. Okay, so correct orientation just means the position, how it was positioned when it collide with each other. So first of all, they must collide. Second of all, they must have minimum the activation energy, so enough energy when they collide. And third of all, they must be at the correct position or correct orientation when they collide with each other. Okay, what are the factors that affect rate of reaction? The same ones that you learned in IGCSE. There's the phase area, the concentration and pressure, and then you have catalyst and temperature, same as IG. Okay, same factors, same keywords. So if you have lower concentration or lower pressure, so the picture is the same, right? If we draw low concentration and low pressure. And if I have another container which has higher concentration or higher pressure, what would be the difference? The difference is that since the one with higher concentration of pressure, there's less space between the particles, it increases the frequency of the effective collision. Okay, take note that you must have the word frequency or per unit time. And you must say effective collision. So I won't accept just collision. You know that effective is a keyword. So both things must be there, effective collision and that per unit time or frequency. Okay, all of those. We're not going to be lenient this time. So take note of this. It's already recorded, so you know what to write. Okay, so if you've increased effective collision per unit time, then the rate of reaction will increase. Okay, and then surface area, it's the chances or probability of when they bump into each other. So if it's a big chunk of reactant or catalyst, so like this big chunk, so there's only like 6 chances that they will collide with each other, which is the 6 phases here. 1, 2, 3, 4, 5, and 6 from the back. Okay, so 6 surfaces. But if I cut, or in other words, I grind my reactants to powder form, or if I grind my catalyst to powder form, then each of this cube will have 6 chances. So there's more probability that they're going to collide with each other. Okay, so it increases the probability of them colliding with each other. Next, catalyst. What does a catalyst do? A catalyst will reduce the activation energy. And you've seen this reaction profile before. Let's just make it simple for now. Just one hump. Okay, no hump. Okay, so the original activation energy without a catalyst was higher. You reduce the requirement for the reaction to happen with lower activation energy, then more particles will possess that amount of energy, more particles will react. So if more particles react, the rate of reaction will increase. Okay, so the new thing here for catalyst is that we need to explain that with the Maxwell-Boltzmann distribution. So you can imagine like there's a beaker of 30 particles. And imagine that as 30 of you in my class. So there's 30 of you. And let's say we divide this into the energy levels. So I'm gonna relate it to, like, say, your result. IB7, IB6, IB5, IB4, IB3, IB2, IB1. Okay, or particles with a lot of energy, particles with lesser energy, and particles with very little energy. Okay, so in a beaker, you will have particles with higher energy and particles with middle energy and particles with lower energy. So in any beaker, you will get different energy levels of the particles in it. So it's same as like your class. Some people get higher marks and some people get lower marks. Some people get 7 and some people get 2. So we're just gonna place whoever gets 7 here and whoever gets 6 here, whoever gets 5, 4, 3, and then we kind of see that, oh, the majority gets 3, and then 2, and then 1. Okay, something like that. So I should be drawing 30 of this, right? 30 of these particles, because there's 30 particles in this beaker, or 30 students in this class. Okay, so I should have 30 of that. So the activation energy, say, is this. Activation energy means the one that achieve that certain energy would be the ones that are higher than this level here, say 80 marks or 80 joules. Okay, so let's say there's this 2. Okay, so 2 people get 7, or like 2 people are above activation energy. So rate of reaction, how do we relate it with rate? Rate is proportional to the area under curve that's above activation energy. So it's like the ones that get 7, those are the ones that reacted. And rate of reaction is proportional to how many students are above the activation energy, or above 80 marks. They get 7. Okay, so what does a catalyst do? Rewind back to just now. So a catalyst reduce the activation energy. So from 80, maybe now the activation energy is 60. So let's say I reduce the activation energy to 60 marks. So more students. So just now these students here got 6, but now I reduce the activation energy. I put a catalyst, or sort of like I reduce the benchmark of getting 7. So now the ones who got 6 just now automatically get 7, because now I say the benchmark is 60 now. Anyone who gets above 60 can get an IB7. So it sort of reduced the benchmark. So this is the new EA. Change the color. EA with catalyst. It's equivalent to like a lower benchmark, a lower threshold for getting IB7. So now those who got 6 just now already automatically get 7, because I reduced the mark for the requirement mark for getting IB7. So that's what a catalyst does. It lowers the activation energy. And this is what a Maxwell-Boltzmann distribution looks like. Okay, the next one is, oh, there's some more about catalyst here. So usage of catalyst is useful because you learn in IG about the reversible reactions, right? So some reactions are exothermic. If the reaction is endothermic, there's no problem. I'm just going to increase temperature to increase the rate of reaction as well as yield of the reaction. So if you've forgotten what is yield, do revise that, because we're getting into that chapter next is the next chapter. The next chapter, we're just gonna go back to entropy first, and then we'll cover the reversible reaction soon. Okay, so you were questioned about yield, and if this is an exothermic reaction, means it releases heat. And when you heat up a reaction to increase the rate of reaction, yes, it does increase the rate of reaction, but a problem will come where it will give you very low percentage of yield. It goes to the left, it shifts to the left. For example, Haber and contact, you covered that in IGCSE, right? So heparin contact, we try not to heat it. I mean, we do heat it a little bit to make it faster, but we try not to heat it too high, because if we heat it in a very, very high temperature, yes, it's faster, but the problem will be that you get very low percentage of yield. So in such cases, that's the advantages of using a catalyst. You also save money on electricity by using a catalyst, because catalyst you can recycle, you can use it again, because it's chemically unchanged at the end of the reaction. So you don't have to spend extra money on buying more catalysts. You don't have to spend on electricity, because it's unchanged at the end of the reaction. Okay, but then don't misunderstand that a catalyst doesn't take place during the mechanism of the reaction. So it will be involved in a mechanism. It's just that by the end of the reaction, it turns back itself. So it remains unchanged at the end of the reaction. Okay, so throughout the reaction, it actually takes place. It actually takes part in the reaction. Okay, there are also biological catalysts called enzymes. We all have them in our stomach. Okay, now I want you to think about, maybe you can pause the video for a while and then think about changing the temperature and imagining this distribution again. Just pause the video for a while. So if you have the same beaker again, and then you have this activation energy, and then imagine these are the people who get 7 on this side, and these are the people who get 6, 5, 4, 3, 2, 1. Okay, if I heat the beaker, still 30 pieces inside, it's equivalent with if I conduct a revision workshop, so people get better results. Same thing here. If you heat this heat the beaker, the particles will possess more energy. So then what happens to the curve, the distribution? So maybe some of those who got low marks just now they've shifted to a higher mark. And those who got this mark just now, maybe they've shifted to a higher mark. Those who got this mark just now, they've shifted to a higher mark. Okay, if I were to draw my curve in this way, okay, you will notice that this area under curve for the red one might be more than the blue one, which doesn't make sense, because before and after I hit the beaker, there should be 30 particles. So same thing, right? Before and after a revision workshop, I should have 30 students. So in order to make the area still the same, you will need to lower the peak. The drawing is not nice. Wait, hold on. Okay, lower the peak. So what does this mean here? It means those with low marks, here's the low marks, right? The number of people with low marks have decreased. Oh, the x-axis, I didn't specifically point out, right? The x-axis is the number of molecules or number of particles with that particular energy. So it's like the number of students that possess that mark. Okay, so the number of students that possess low mark has decreased, and the number of students that possess high marks have increased. But look at this, the EA is undisturbed because we didn't use a catalyst. This time we just added, we just heat. We didn't add any catalyst, we just heat it up. So a lot of the particles have more energy now, but the EA is the same. But do you see the area under curve originally was lower? And the area under curve, after you heat it up, now it's higher. So again, I'd like to point out again, the rate of reaction is proportional to area under curve above EA. Okay, or we can also say the proportion of particles. Proportion of particles that possess EA or more. More than or equal to EA, then they will react. Therefore, they will increase the rate of reaction. Okay, so our focus here would be the black color curve. So this is the original curve. This must represent 30 of you, 30 particles or 30 students. And after a revision workshop or after heating the beaker, more particles will have higher energy. So at those that got lower energy or those that got lower marks have decreased. And those that got higher marks have increased. And if here was the activation energy, now there's more. So originally just this portion can react. Currently, now this whole portion can react. So the area has increased, which means the rate of reaction has increased. That's all you missed for SL portion.